Okay, yeah. In terms of other announcements, homework 2 is due tomorrow. A couple requests. So if you use Cam Scanner to take pictures of your homework, please use the feature that allows you to turn it like unprojected, I guess, and make it black and white, because it makes it way easier for us to grade. Otherwise, with the picture, there's glare, this, that, and whatnot. So please use that feature that allows you to bring it immediately in front of the camera and turn it black and white. And also, please submit it as a PDF. Sometimes it gets a little weird when you submit the images themselves. So if you just have the images, what you could do is you could put them into Word or Pages and export as PDF. Okay? And as I mentioned, quiz solutions will be out tonight. Hopefully it wasn't too bad. And the grades will be out by Tuesday. So before the next time we meet, ideally the grades will be done. Okay? And feel free to reach out, whether it's before the grades come out or it's after the grades come out. If you have any concerns with how you're doing in the class or just want to talk. If you can't make it to my or any of the other office hours, or you want to speak to me in particular, you can just email me and we can set something up. Sounds good? Okay. So now, let's actually start talking. Oh, did I? Go ahead, I'm screwing. Okay. Now let's actually start talking about what a proof is and look at some examples of formal proofs and different types of proofs. Okay? So, if we want to be formal, we can say a proof is a set of it's a sequence rather, of finite steps, which when we combine them in a specific order, tell us the truth of a specific statement. They tell us that some statement is true, right? But more colloquially speaking, a proof is an argument that convinces a reader or someone else that a statement is true. Okay? And in most proofs, we're given some amount of information that we're allowed to assume. Either it's given to us in the question, or we're allowed to assume it based off of things that we already know to be true. By the properties of integers or rational numbers, for example, things that are true by default in all situations. And starting with that information, we'll make some series of steps, arriving at some proposition that we have shown to be true. Okay, so we'll start off with some information that we're allowed to assume and make a valid series of steps that imply that the statement that we want to prove is true. Okay, and sure, we can say this and write some symbols, but the only way we'll learn is by doing some examples. So that's why for the next week and a half, 2 weeks, we'll be doing a lot of examples. Okay, because that's really the only way to learn how to do proofs. Okay, and you'll sort of pick up the pattern that there is. Okay, so there are several types of proofs. There are direct proofs, which are they can really entail anything. There's no one type of problem that falls into any of these buckets. But direct proof is sort of when we don't do any of the other types of proofs. There's a proof by contradiction, which we'll talk about shortly. A proof by contraposition. And this should sound familiar because we learned about the contrapositive on Tuesday. And so we'll use that. And remember, we saw that the contrapositive of a statement is equivalent to the original statement. So we could use the contrapositive to help us prove things. We could also break our proof up into different cases and do separate proofs for each of these individual cases and show that the union of all these cases proves the statement for all, in all cases, really. And then there's this idea of proving things by induction, which will be very similar to recursion, which you will have talked about in 61A. But we'll probably only start talking about about induction a week from now, next Thursday. So today and next class, we'll talk about up until here. Okay, and then induction is like a different beast. So we'll start talking about induction a week from now. So any questions with the overall landscape of this? Okay, so we can start talking about, before we talk about direct proofs, there's this new notation I want to introduce. So A vertical bar B, which you read as A divides B, essentially tells you that A is a factor of B. To be formal, it tells you that there exists some integer C such that B is equal to A times C. Okay? So, for example, what we could say is 8 divides 24 because there exists some integer that I can multiply 8 by to get 24. Is that clear? But I could not say 5 divides 24 because there's no integer that I multiply by 5 that will give me 24. So in this case, I would say 5 does not divide 24. Is that clear? So A divides B means there's some integer that I can multiply a by to give me b. Okay, notice we said integer, not necessarily natural number, right? So these could be negative integers as well. Okay, so we'll use that heavily today. We'll talk more about divisibility and primality after we talk about induction, but most of the examples that people like to use for these sorts of things involve divisibility, so that's why we'll introduce it now. And there's another idea that we need to talk about. It's how we represent even and odd numbers. Right? We all know an even integer is some integer that can be written as 2 times some other integer. Right? It's just a number that has a factor of 2. So we'll often use 2k to represent an even number. And if we want to show that some quantity is even, we have to show that we can write it as 2 times some integer. Is that clear? And similarly, if we want to show that something is odd, we have to show that it can be written as 2 times some integer plus 1. Or equivalently, 2 times some integer minus 1. Right? Because the even numbers are the numbers that can be written as 2 times another integer. And when you add 1 or subtract 1 from an even number, you'll get an odd number. So 2k plus 1 and 2k minus 1 we use to represent odd numbers. Okay, any questions with all of this? No? Okay. So first we'll talk about direct proofs. Okay? In a direct proof, again, as I mentioned before, is really a proof where it's essentially all the proofs that are not contradiction, not contraposition, and not induction, not cases. Okay, it's sort of where we prove something just starting off with the information that we're allowed to assume, and then make a valid sequence of steps from there. Okay? And oftentimes, our direct proofs will look like an implication. If blank is true, then show that this other blank is true. And we just start off with the first blank, we start off with A, do some series of steps, and get to B. Okay? So, the best way to learn is by doing an example. So we want to prove that if x divides y and x divides z, then x divides y plus z. Okay, so we're proving that if x divides y and x divides z, then x divides y plus z. So does anyone have any ideas? And of course, x, y, and z are all natural numbers. Does anyone have any ideas on how we can start this? If we know that x divides y and x divides z, what can we say? From the definition of this divides notation, what can we say? Anyone? Yeah.
We could say, like, using the definition of divides notation, that there exists some c such that y equals x times c.
Good.
And we can also say there exists some other variable, d, for example, such that z equals x times d.
Good. We know that since x divides y, there exists some integer such that y is equal to c times x. And since x divides z, there exists some other integer. Well, we don't necessarily know that y and z are different, but that doesn't really matter for now. There exists some integer such that z is equal to d times x. Okay, so this is what we're allowed to assume. And if we want to be super explicit, we can say c is, by the definition, c is an integer. And d is an integer. But, I mean, of course, since I said x, y, and z are natural numbers, c and d will also be natural numbers because they can't be negative, right? And now we want to show that we can write y plus z as some integer times x, right? Because that's equivalent to x dividing y plus z. We want to somehow show that we can write y plus z as some integer times x. Is that clear? Okay? And so what can we do? Well, we can add the two equations that we have, right? So we add y plus z, and on the right-hand side, we have cx plus dx. But we can common factor out the x, and we have c plus dx. Okay? And so what we've done is we started off with the information we were allowed to assume, put it together without any mathematical, flaws in logic, like everything we did here is valid. We didn't do anything like divide by 0, for example. And our result is that we can write y plus z as some integer times x. So since c and d are integers, c plus d will also be an integer. So since c plus d is an integer, or I can even say this, since c plus z and z, x divides y plus z. Is that clear? So we've proven now that if this condition holds, then x divides y plus z. And what we'll like to do oftentimes is write like a concluding statement. So saying, therefore, since c plus d is an integer, x divides y plus z. And you'll see, basically anytime you read a proof, there will be this concluding sentence at the end, just to sort of wrap up what we were talking about. So any questions with this? Yeah.
What's the difference between like the upside triangle Gauss and the lower, like the bottom triangle Gauss?
Sure. So the one you'll see most commonly is this one, and that says therefore. The inverted version of that says because. Okay? But I personally never use the because one. You might see it out in the wild, but therefore is pretty common. Okay? So, what's happening? Okay. Let's look at another example. So now we want to prove that for any natural number n, 3 divides n cubed minus n. Okay, so I'll tell you, there is a way that we could do this by breaking up n into 3 cases. Okay, but we haven't really talked about cases yet. So I'm telling you that this can be done without looking at cases. Okay? And so another piece of notation you should be aware of is this acronym RTP. What does that mean? It means required to prove. Okay, and I use this a lot. Required to prove. And essentially what we're required to prove is that n cubed minus n is equal to 3k for k being an integer. Is that clear? So that's what we're required to prove. And so how we'll actually do this is not immediately obvious, right? And again, I mentioned we could break this up into cases, but for this one, we need to be a little creative. Okay? Suppose this weren't, I don't know, a discrete math class, and you were in, I don't know what Americans call it, I guess Algebra 2, Calc, something like pre-calc, trig, something like that, and whatever it is, and you saw this, and you were learning about factoring. What would you factor this as? So the first thing you'd factor out is the common factor of n, right? Okay? So I can say this is n times n squared minus 1. Okay? And then how can we factor this even further? Exactly. We will use the difference of squares, which if you haven't seen it, that's fine. Difference of squares. It says x squared minus y squared is x minus y, x plus y. Okay, so we'll employ that. So we have n minus 1, n plus 1. Okay? And now I'm going to arrange them in a very specific order. Okay? So I'll arrange them as n minus 1, n plus 1. Okay? Do you agree that n minus 1, n, and n plus 1 are 3 consecutive integers? Okay? Now let me write out the integers from 1 through 10, and let's see what we notice. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Okay? And so what's interesting is that I can pick any 3 consecutive integers. Okay? So for example, why don't I pick 5, 6, and 7? As there another example, why don't I pick 9, 10, 11? Okay, and there's a third example, why don't I pick 3, 4, 5? what do you notice about all three groups of consecutive integers? Yeah.
One of them has to be divisible.
One of them is always a multiple of 3, right? An easy way to think about this is if we're looking at even numbers, i.e. multiples of 2, if you have any two consecutive numbers, one of them has to be even and the other will be odd, right? So similarly, if I have 3 consecutive integers, one of them always has to be a multiple of 3. If I have 10 consecutive integers, I'll always have one of them being a multiple of 10. Is that clear? And so what we'll say is that any 3 why don't we put this over here? Consider any 3 consecutive ints, one must okay, so one of them has to be a multiple of 3. Okay? That means in this product, either n minus 1 has a factor of 3, or n has a factor of 3, or n plus 1 has a factor of 3. Right? And I guess you could technically think of those as being 3 separate cases, but we know it's essentially the same case in each of these. There will be some factor of 3 here. Okay? Maybe there's a factor of 9 if we had 9, 10, 11, for example. It wouldn't be just 1, 3. But we know for sure there has to be at least one factor of 3 here. So we know we could write this as 3 times k, where k is some integer. Yes, in the back.
So what was actually required to say the statement, consider any 3 consecutive like that? Because we just showed it on the number line from 1 to 12, right? That 3 of them are...
Right. That was just an example to show it to you. It's more of a property that just holds true.
Okay, so we just assume that's true.
Yeah, that's something that you can state to be true.
Okay.
Yeah. Yeah. And recognizing that trick almost is the key to this proof. And there are other ways you can do this proof without knowing that trick. But that's essentially a property that you can assume to be true of the integers. Right? And there isn't any formal proof that you really need to do to convince yourself of that. Right? I convinced you that it's true in all cases. Right? There was no specific casework that was. I could have given you the numbers from 1,000,000 to 1,000,000 plus 10. Right? There's nothing specific about this set of numbers I gave you, and we know it's true for any set of integers. You had a question?
Yeah. So if we adding on what you said.
Yeah.
So we used examples to deduce the actual trick, right?
Right.
But examples won't have a rigorous proof in a way,
Right.
Because we see that it's in 3 numbers we've got 1.
Yeah.
But we don't really know in the number line there could be 3 numbers that don't have that specific property. So is there a mathematical way we can describe the n minus 1 thing to show that it's always going to be the case for n belonging to natural numbers? Okay,
so you're saying, what if you're not convinced that this property holds true? What if somewhere down the number line this didn't hold true? Why don't we wait about a week and a half or 2 weeks to talk about that? Because then we'll start talking about modular arithmetic, and then maybe I could give you a more complete argument. Okay, but essentially, what you'll see is that if you look at any 3 consecutive integers, they'll be of the form 3k, 3k plus 1, and 3k plus 3, 3k plus 2. Okay, you'll have one of each of those. And when you multiply those out, you'll always have a factor of 3. Okay, because every integer is either 3k, 3k plus 1, or 3k plus 2. It's either, the remainder when you divide it by 3 is either 0, 1, or 2. Okay, and it's totally fine if you don't see where this plus 1 and plus 2 is coming from, because we haven't really talked about that yet, and we probably won't until after we finish induction. But there is a way to formally prove this if you're interested in that. But for our purposes now, let's assume that to be true. Okay, so we have this property of the integers that any 3 consecutive integers will contain a multiple of 3 if you multiply them out. So that means this product, n minus 1 times n plus 1, will have a factor of 3. So therefore, we've shown that in all cases, n cubed minus n will have a factor of 3. And therefore, 3 divides n cubed minus n. Is that clear? Any questions with this? Yeah.
So do we need to write like the examples and stuff, or is just everything that's kind of in that like red, brown color, is that the actual like proof of it?
So why don't I even just erase this? Okay, because the example is not part of the proof. That was sort of just to illustrate to you this property that happens to hold true. Okay, you'd have to include what I've written in the blue as well, like this area as well, if you're talking about how you'd actually write this.
Okay, so you do have to.
Yeah, that's something that you have to state, yeah. What's in this cloud, I guess, is a separate property that I'm telling you for now you could assume to be true, but that could be a separate question, like prove that that property is true. But that's not part of the proof. The example is just for me to make you aware of that property existing. Okay, any other questions with this? Because I want to move on and try and get to a couple other proof techniques while we're here. Okay? So the next one is proofs by contradiction. Okay, so in a proof by contradiction, suppose we want to say it proves that some statement S or proposition S is true. Okay? What we'll do is we'll begin by assuming whatever we can from assuming that not S is true, i.e. we'll assume that S is false. Okay? And what we'll do is we'll do our manipulations and get out from whatever our statement, whatever we can assume, and at some point we'll reach a contradiction. Okay? So we'll start off by assuming that our statement is false, even though we want to prove it to be true. We'll start off assuming it's false and arrive at a contradiction. Okay? But if we've arrived at a contradiction, that tells us that whatever we assumed, the opposite of that has to be the case. Okay? But we assumed not S to be true, and now this is telling us that not S is false. But a variable can't be both true and false at the same time. So this is a contradiction. Okay? And so this tells us that whatever we assumed in the beginning, the opposite of that has to be true. Okay? And if the opposite of what we assumed is true, and we assumed not S, that means S has to be true. Is that clear? So suppose we wanted to prove that all dogs are mammals, for example. We would start off by assuming not all dogs are mammals. And then, we'd deduce from that whatever we could, and then end up at some contradiction like the world is flat. But since the world is not flat, that's a contradiction, then the original thing we assumed is false. And since we're assuming the opposite of what we want to prove, the opposite of the opposite is true, meaning that our original statement is true. Is that clear? And this will make a little more sense when we look at some more examples. Okay, and oftentimes we'll use the idea of a proof by contradiction to show that there doesn't exist something, the non-existence of something. Okay? Because it's very easy to take the negation of that and say that this thing exists. But it's very hard to say, come up with infinitely many examples to show that this does not hold. Because you can't do that, right? We need something that's rigorous, that holds for all cases. And so let's look at an example, because I think that'll make things a little more clear. So for example, let's prove that there is no greatest even integer. Okay, so we want to prove that there's no biggest even integer. Okay, so we'll do this as a proof by contradiction. And usually when you do a proof by contradiction or by contraposition or by induction, you'll actually write, let's proceed by proof by contradiction, just so it's clear what you're doing. And let's say, assume n is the greatest even integer. Is that clear? So we're going to assume the opposite of the statement. We're going to assume that there is a greatest even integer, and let's call it n. Okay? Then let's construct, we can say since n is even, n is equal to 2k for some other integer. Is that clear? Since it's even, I can write it as 2 times some other integer. Let's say consider m, which is a new number that I'm creating, which is equal to n plus 2. Okay? Well, I can write this. So two things. So one, we agreed that this is greater than n, right? Because we're starting off with n, and I guess we can say natural number, so that we don't have to consider the case where this would be negative, but why would it be? Okay? We have n, we're adding 2 to it, so we know that this has to be greater than n. But is it even? Well, yes, because n was 2k, and we're adding 2 to that, so now we have 2k plus 1. And so what do we have from this? M is even and greater than n. This is a contradiction. Why is it a contradiction? Because we assumed that n was the greatest even integer. And we just showed that m is an even integer that's even bigger. Okay? And so we've arrived at a contradiction, and therefore, our initial assumption that n is the greatest even integer is false. So what this is a proof that there's no greatest even integer. I can even erase that. So it says, therefore, there is no greatest even integer. Is that clear? We started off by assuming the opposite of our statement and arrived at a contradiction. Yeah.
Okay, so if n is the greatest even integer,
Yeah.
then can you say that you can add 2 more to that? Like, what allows you to say that?
Well, we can call it the greatest even integer, but it's still an integer. And you can add 2 to any integer. Right? And that's sort of part of the proof. Right? If we assign a variable to it, we say it's the greatest even integer, but it's still even and it's still an integer. And we can add 2 to any integer. Any other questions? Okay, I want to look at another example, which is like the standard example for doing proofs by contradiction. Okay? And if you were to even Google proof by contradiction, this is probably the very first one that you would see. Okay? So we want to prove that the square root of 2 is irrational. Okay? And so what are we going to start off by assuming? We're going to assume that it's rational, right? Proof by contradiction. Assume root 2 is rational. And if it's rational, what can we say? You can write it as the ratio of 2 integers, right? And so we'll assume square root of 2 is equal to a over b. And just so that we know a and b are unique, let's assume that they're in reduced form. Okay? So we're a and b in reduced form. Another way of saying this is they share no common factors. Okay? Just like 4 over 8 is equal to 1 over 2. We're going to say this is the lowest form of this. Okay? What I'll do now is square both sides. And I'll have 2 is equal to a squared over b squared. Is that clear? So I started off by writing root 2 as a over b. I squared both sides. Square both sides. And what I'll do now is multiply over the b squared. Okay? Now I have a squared is equal to 2 times some integer. What does that tell us? From like the third slide that we looked at today. A squared is equal to 2 times some integer. Because b squared is an integer. So what does that tell us? Yeah, so that tells us that a squared is even. Is that clear? Because a squared is 2 times something. Therefore, a squared is even. Okay? And I guess theoretically this is another separate property that you'd have to prove. Maybe it'll be an exercise in your homework. But for now, we can take it for granted. Just assume that if a squared is even, then a is even. Is that clear? Okay. can assume A is even. Is everyone convinced that that's true, by the way? If some square is even, the initial number, the square root of it has to be even as well? Okay, if you're not convinced, we can walk through a proof of that after. But it is a property that I'm sure you've assumed to be true before. Okay? So we have A squared is even, but that allows us to assume that A is even. Is that good? Okay? But if A is even, we can say A is equal to 2k for some other integer. Let's just say A, B are the integers here. Is that clear? So now since A squared is even, I'm saying that A is even, which allows me to say that A is equal to 2 times some integer. I'll call that k. Is that clear? So now, going back to our original equation, we had A squared is equal to 2b squared, and I'll substitute A is equal to 2k. So now we'll have 2k squared is equal to 2b squared, which gives me 4k squared is 2b squared, and I'm left with 2k squared is equal to b squared. Okay? So I'm assuming that A squared being even gives me that A is even. If A is even, I can write it as 2 times some integer. I plug in that representation, 2k, into A squared is equal to 2b squared, do some reduction, and I'm left at this line, which tells me b squared is equal to 2k squared. What does that tell us? B squared is even, right? Because that b squared is equal to 2 times some integer. So b squared is even. And again, we're assuming this property to be true. Therefore, b is even. And that tells us we can say b is equal to 2 times, why don't we say c, for c being another integer. Can anyone spot the contradiction? Yeah.
If they're both even, then they're not in the reduced form.
Exactly. So this is a contradiction. We assumed the greatest common divisor of A and B to be 1. But now we showed that both A is even and B is even, which means their greatest common divisor is at least 2. Right? But showed they share a factor of 2. Yeah.
When we say that A squared is even, implies A is even.
Yeah.
So let's say A squared is equal to 6,
Sure.
which is even.
Yeah.
But like A is going to be root 6, right? So how does that imply?
For integers, A and B.
So like, so does A squared have to be like an integer as well?
Yeah, well, here we assumed A and B are integers.
So if A squared is an integer, and that's even.
Then A will be an even integer as well, yeah.
Okay.
Yeah. Okay? And so we assume that A and B are in reduced form, but then we show that A has to be even and B has to be even. This means that they share a factor of at least 2, which means that they weren't in reduced form, and that's our contradiction. Therefore, root 2 is irrational. Is that clear? Okay. There's another example. I'll probably skip this for now just because I want to get to the next proof technique, but I think you should try it on your own. Prove that in any set of n numbers, there is at least one number that is less than or equal to the mean. And if we're doing this by contradiction, what would we assume? There's no number that is less than or equal to the mean. And then what we'll show is, I guess I can do this relatively quickly. So assume all are greater than the mean. And what we can say is, let our set be x1, x2, all the way until xn. If they're all greater than the mean, then that tells us x1 is greater than x1 plus x2 plus xn over n. x2 is greater than this quantity. So on and so forth. And once you get to the last one, what you can do is add both sides of the inequality. On the left side, you had x1, x2, all the way until xn. So that sum gives you x1 plus x2 all the way until xn. Greater than sign. Now we're adding up n times this sum divided by n. Right? It's almost as if we add 1 over n times, we'll get 1. So then the quantity on the right-hand side is the same thing. But one number can't be greater than itself. So this is a contradiction. Is that clear? Because one number can't be greater than itself. Okay, let's talk quickly through proofs by contraposition. Okay, and now suppose we want to prove that P implies Q. Okay, and most cases in which we do a proof by contraposition, the structure will be clear. If blank, then blank. Okay? Remember, proving that this is true is equivalent to showing that this proposition holds a true value. Okay? And that's equivalent to showing that its contraposition holds a true value. Right? Because we showed previously that P implies Q is logically equivalent to not Q implies not P. Right? So if our goal is to show that this is true, we can instead just show that the contraposition is true. The contrapositive is true. And that's the same thing. Okay? A cool side effect. Did you have a question? Okay. Is almost always we'll look at this first case. We'll assume P to be true and then show that Q is true. Okay? But also notice that the implication takes a true value in these last cases as well, whenever P is false. Okay? So another thing you could do is, like, for example, a proof could be if all dogs could fly, then 2 is greater than 3. That statement itself is true because the thing you're assuming, P, that all dogs can fly is false. Right? And so the implication is true. But that's not telling you that Q is true on its own. It's just telling you that if all dogs could fly, then our universe is probably broken and maybe 2 could be equal to 3. Is that sort of clear? And we'll talk more about that next week. I wouldn't worry too much about it right now, but just to get you thinking. In 99% of the cases, we'll be looking at this one in the beginning. P will be true, and we'll show that Q is true. Okay, so let's dive into an example. Okay, so suppose we want to prove that if x squared minus 6x plus 5 is odd, then x is even. We can actually do this with a direct proof, but the contraposition one is much cleaner. Okay, and because we're running out of time, I'll do the contraposition one first, and at the end I'll scribble down the direct proof, and we can get through as much of it as we can. Okay. So what's the contrapositive of this statement? So the initial is if x squared plus 6x plus 5 is odd, that implies that x is even. What's the contrapositive? Yeah, if x is odd, remember this is P and Q, so our contrapositive is not Q implies not P. And so what's Q? It's that x is even. So not Q is that x is odd. So you want to show that if x is odd, then this quantity, x squared minus 6x plus 5, is even. Is that clear? We originally wanted to prove P implies Q. Now we're assuming not Q, and we'll somehow get to not P. Is that clear? Okay. Well, if x is odd, you can say x is equal to 2 times some integer plus 1. Right? And you've probably noticed by now, this is a common theme. To say that something's odd, we'll say x is 2k. To say that something's if x is odd, we'll say x is 2k plus 1. And to show that's even, we'll say x is 2k. We really don't have to use k. We could use 2a, 2n, whatever. But k is usually the variable we use here. Okay? So now we have that x is odd. And now we want to show that this quantity is even. So what do? Let's just evaluate it. Okay? X squared minus 6x plus 5. What does that give us? Well, that gives us 2k plus 1 squared minus 6 times 2k plus 1 plus 5. Is that clear? And now we need to evaluate this. 4k squared plus 4k plus 1. Okay. Minus 12k minus 6 plus 5. Okay? And our end goal is to show that this quantity is even, which is equivalent to showing that we can write it as 2 times some integer. Okay? So let's do a little bit of simplification first. Okay. Let's group by like terms. We have the 4k squared, then we have the 4k minus 12k, so we're left with minus 8k. Then we have 1 minus 6 plus 5, and I believe that goes away. Yeah. And so we're left with 4k squared minus 8k, which we can factor out as being 2 times 2k squared minus 4k. We know since k is an integer, you square it, that'll still be an integer. Multiply it by 2, that's still an integer. Minus 4 times k, that's still an integer. That property, by the way, is called closure. The fact that if you add and multiply any integers, the result is still an integer. Right? Not that that's important, that's just for you to know. This is some integer. Right? And therefore, if x is odd, we can say that x squared minus 6x plus 5 is even. And we'll say, therefore, original statement holds by contraposition. Okay, so let's recap. What did we do? We wanted to show that if this quantity is odd, then x is even. What we did was we said, let's instead prove the contrapositive. Okay, so instead we assume that x is odd and that quantity is even. So we reversed it. Okay, and that makes it significantly easier, right? Because how would you go about proving that quantity is odd? Okay, you can do it, and the way you do it in a direct proof is actually by factoring it into x minus 1 times x minus 5. Okay? If you want to try it on your own, you'd write it as x minus 1, x minus 5. And you notice that if that's odd, the two constituent products have to be even. Okay, and you could do some casework with that. But it's significantly easier and more straightforward to do this one with the contrapositive. Okay? And so the question is, why does the contrapositive even exist? Well, it's because in cases like this, it's a lot more straightforward. It's a lot more clear how we'll approach the answer. Right? Because if we know something just about x, it's easy to derive something about x squared minus 6x plus 5. But it's hard to go in the opposite direction. Okay? Enjoy your long weekend. The quiz solutions will be posted tonight. And yeah, feel free to reach out if you have any questions.